Okay, going to get started. Today's class, we're carrying on with discussions of magnetism. We introduced magnetism and magnets in last Tuesday's class, and we talked about forces, magnetic forces on electrical currents and moving charges in last class. In this class, we're going to talk about how the magnetic fields that cause magnetic forces are created by electrical currents and moving charge particles. So basically, we're going to work through a few examples, a few illustrations of magnetic fields created, manufactured by electrical currents. And there are going to be some famous examples of magnetic fields created by electrical currents. There's the magnetic field of what we just call a long straight wire. There's the magnetic field of what we just call a current loop, a circular loop. And then there's the magnetic field of what we call a solenoid. I'll explain a solenoid later on. And so that's the basic topic for today. I just listed them here. So for a long straight wire, if you want to think of an example or an illustration of a current carrying long straight wire, think of a current carrying power line. And so it's the magnetic field that's created by that power line that we're going to be investigating today. When we talk about the magnetic field of a current loop, so a wire loop carrying electrical current, we'll discover that the magnetic field of a wire loop carrying a current looks like the magnetic field of a bar magnet. And actually we'll discover that a bar magnet is really a current carrying loop. The little charged particles, the little electrons inside the bar magnet are running around in a little current loop in the bar magnet. And we'll learn that, we'll discover that by looking at the magnetic field of a current loop. And then finally, we're going to talk about the magnetic field of what we call a solenoid, particularly a long solenoid, a long current carrying solenoid. And the importance of that magnetic field, it's really a very special magnetic field, is that it's a uniform magnetic field, same size, same magnitude, everywhere inside the solenoid. Before we look at those examples, though, I just want to mention that the realization that electrical currents create magnetic fields and hence cause magnetic forces, that realization that currents were the source of magnetic fields and created magnetic forces was kind of this momentous realization in physics history and scientific history. And so just that basic idea, we didn't mention it in the last class, really, where the magnetic fields that were coming from that were causing the magnetic forces. But now we are mentioning it. They're coming from electrical currents that are creating the magnetic fields that create the magnetic forces. And so that was a huge event that propelled electricity and magnetism forwards. The person that discovered it, and he sort of accidentally discovered it, or he kind of accidentally realized it, was Hans Ørsted. So he was a Danish scientist. This was, more than 150 years ago now, almost 200 years ago now. And as I say, it was really a breakthrough that ultimately led to kind of the realization that electricity, which is due to charges, and magnetism that's due to currents, are interconnected. And it also led to a lot of work, a lot of effort on figuring out the magnetic fields that are created by different arrangements of currents, like the long straight wire, like the current loop, like the stuff we're going to do today. I see a question in chat. Are currents the only sources of magnetic fields? That is actually a brilliant question. So Mohammed is also on the path to being a great scientist. So let me first say that electrical currents and moving charges, which are electrical currents, are both sources of magnetic fields. But actually, within the next couple of weeks, we're going to be discovering another source of magnetic fields that is a huge breakthrough, and it's actually going to be electrical fields can make magnetic fields and vice versa. I'm not going to say any. I wanted to keep it as a surprise. I can't keep it as a surprise now. So later on in the course, we're going to find this relation between electric and magnetic fields, and that was a great question about that. Okay. In this little overhead here, let me get the pen working. I'm not using the pen at all. So in this little picture over here on the left-hand side of this slide, I've got a current carrying straight wire. That's the vertical line here, or the vertical wire here. And surrounding in the neighborhood of this current carrying straight wire are tiny iron filings, very small iron filings. And iron filings in a magnetic field, these little flakes of iron in a magnetic field, they get magnetized by the magnetic field. And it does a couple of things to them. It causes them to line up with, orientate with the direction of the field. And it causes them to move to regions where the field is strong, away from regions where the field is weak. And so these little iron filings, I know they're not alive, right? But it's like they are alive in a magnetic field. They turn to line up with the field lines. They move to regions of large magnetic field. In that way, they map out. They map out the magnetic field. So if you look in this sketch here, you see that the filings are kind of forming concentric loops around the wire. And you also can see that filings tend to congregate. They will congregate in the regions of stronger magnetic field. And they will actually move away from the regions of weaker magnetic field. So here they're going to congregate near the wire, move away from regions far from the wire. And those filings are really mapping out the field. They're really showing us the field. They're demonstrating to us the magnetic field of the long straight wire. So they form concentric loops because the field lines are concentric loops. And they'll move closer to the wire because the field is stronger closer to the wire. And so they really are a map, this sort of beautiful map of the magnetic field. Okay, so that's one way of seeing a magnetic field. Here's a second way of seeing a magnetic field. It's with compasses. So imagine, I think of compass, I think of some sort of boat out in the ocean and trying to find my way back home. Or I'm lost in the forest and I'm trying to find my way back home. So compass orientates in magnetic fields. And normally we use a compass if we're lost in the forest or we're lost on our boat to tell us which way is north. But we can also use a compass to illuminate the magnetic field, say, of this long straight wire in this particular drawing. So in this sketch over here on the left, again, I've got a long straight wire and I've got an array of compasses. I don't know if that's plural of compass, but let's pretend it is. Compasses around the current carrying wire. And just like on the boat or in the forest, the needle will point in the direction of the magnetic field. These compass needles are pointing in the direction of the magnetic field, and they map out a concentric loop of field lines around the current carrying wire. And they would experience a stronger alignment of the compass needle if they're close to the wire, and a weaker alignment of the compass needle if they're far from the wire. So they're also influenced by the strength, the magnitude of the magnetic field. And so the compass needles, like the iron filings, are mapping out the magnetic field. They're demonstrating the magnetic field. They're showing us the magnetic field. The magnetic field lines here are concentric loops around the wire. The magnetic field is stronger close to the wire, it's weaker further from the wire. Okay, I want to quantify the magnetic field of a long straight wire. I want to say something quantitative about the direction of the field and about the magnitude of the field. Let's start with the direction. This slide's about the direction, and then we'll go on to the magnitude. The next slide will be about the magnitude. And you're going to love this one. You're going to absolutely love this. There's another right-hand rule. There's a right-hand rule for the circulation or the direction of the magnetic field around a long straight current carrying wire. And I think I would suggest, rather than look at my right hand, which in the camera looks like my left hand, look at the sketch. I drew that sketch of my right hand. And in that sketch, I'm showing you how to use the right hand rule and demonstrating how to use the right hand rule to figure out which way round, clockwise, counterclockwise, the field lines, the magnetic field lines of the long straight current carrying wire loop. Do they go clockwise? Do they go counterclockwise? And so the trick with the right hand rule, or the rule with the right hand rule, is to grasp the wire, which you see in the slide. I'm grasping the wire with your fingers curled with your thumb pointing in the direction of the current. So I've grasped the wire with my thumb pointing in the direction of the current. In this example, the current is upwards, so my thumb is pointing upwards. Then your fingers of your right hand naturally curl. Let's hope so. Naturally curl in the direction of the field lines. And so you see they're curling such that they, over here on the, left of the wire, the field lines are coming out of the slide. And over here on the right hand side of the wire, the field lines are going into the slide. And that's how the fingers on this sketch are curling. They're coming out on the left-hand side. They're curling back in on the right-hand side. If I was to reverse the direction of the current, right now that current's going straight up. If I was to reverse the direction of the current and have it going straight down, then when I grasp the wire with my right-hand rule to find out the field direction, I would grasp it such that my thumb points down, and my fingers would therefore curl the opposite way, and they would come out on the right-hand side of the wire and go into the slide on the left-hand side of the wire, i.e. the field would be in the opposite direction. And so that's how you get the direction. Okay, so there's a question. That's an important question. Again, Mohammed is our question master for today. So that's great. And this is a good question too. There is more than one right-hand rule. I know you thought the right-hand rule was awful. I had a few discussions where I got that feeling. But just to make it even worse, there is more than one right-hand rule. There's the right-hand rule that we were talking about in the prior two classes, which, as Mohammed says, is about the direction of the force. That right-hand rule, you pointed the palm of your hand in the direction of motion of the charges or the direction of the electrical current. You curled your finger in the direction of the magnetic field, and the thumb gave you the direction of the force. So that is a right-hand rule for magnetic forces. This is the right-hand rule for the direction of the field lines of a long, straight current carrying wire. So it's a second right-hand rule. And I don't want to sink your boat or whatever the right expression is. Even worse than this, we're going to meet a third right-hand rule in this class. We'll meet it in the second half of the class. So there's more than one right-hand rule. Now, I actually think, this is an easier, more straightforward right-hand rule because it's really just about the relationship between the direction of the current and the direction of the magnetic field for a long, straight current carrying wire. You've only got to worry about pointing your thumb in one direction, curling your fingers, and seeing what direction they curl. But that was a good question.
I hate to keep bothering, but more so on that same question, isn't this picture defining both magnetic field? So magnetic field would be going up with the thumb as well as curled in with the fingers? Because isn't B magnetic field?
No. So I'm just going to put in my headphones. I realized I didn't put them on. So this right-hand rule, all it's telling you and all it's about is you point your thumb in the direction of the current and your fingers are curling in the direction of the magnetic field. There's no magnetic field upwards or downwards when you do that. So if you look at that sketch of the right hand, there's just a thumb pointing upwards in the direction of the current, and there's just fingers curling around the wire in the direction of the field. Does that answer your question?
Yeah, that makes sense. Thank you.
Okay. It's really good that you're asking these questions because I'm sure 90% of the class is wondering, well, what on earth is he talking about? So it's important we get these right-hand rules straight because they once you know them, they're really helpful. But if you don't quite know them, they're really confusing. So Matthew says, so could you say the first right-hand rule is for the linear force and this one is for the circular motion of a field? I think you could say it like that. I might say it slightly different if in my words. The first one was really the relationship between the direction of the current, the direction of the field, and the direction of the force, between those three things. And that one applies to any current in any magnetic field. This one is much more, I think of this one as much more specific. It's specific to a long, straight current carrying wire, and it's just a relationship between current and field. It says nothing about forces. Okay, so that was the direction. And this slide is about the size, or this slide is about the magnitude of the field. And this equation on this slide tells you the strength of the magnetic field, so the magnitude of the magnetic field in Teslas, as a function of the current that's flowing in the wire. So that's the I here. And your distance, your radial distance from the wire, that's the R here. So you see the I in the picture, you see the R in the picture. And so it's telling you the field strength, magnitude, size, as a function of current and distance. There's a constant in this equation. Here we are. The permeability, magnetic permeability of free space. It's kind of got the language like the electric permittivity of free space. And it's the magnetic equivalent that characterizes the strength of magnetism for that electrical parameter that characterizes the strength of electricity. And its numerical value is written down here, is 4 pi times 10 to the minus 7. And the units are Teslas, meters, amps. Those are the units that make this equation dimensionally correct. Look, the equation has embedded in it a number of things. We'll look at an example of it. But it tells you if you've got more current flowing in the wire, you're right, you're going to get a stronger magnetic field. Well, I think we all probably knew that. If you're further from the wire, you're going to get a weaker magnetic field. We might have all guessed that. But it specifically tells you that the field is in proportion to the current. Doubling the field, doubling the current doubles the field. And the field is in inverse proportion to the distance. So doubling the distance halves the field. We might not have guessed that. I doubt that we would have guessed that. Okay, I want to demonstrate this magnetic field. So I'm going to share a different screen here. So I hope you can see a video that I'm going to play. In this video, in red here, this is a long, straight current carrying wire. I hope you can see my pointer. Yeah, I think you can. Surrounding it are compasses with compass needles. And we said that compass needles, the needles will point in the direction of the magnetic field. They can map out the magnetic field. Over here on the bottom left, this is a switch. And with this switch, I can turn on the circuit firstly. And then secondly, if I push the switch forward or backward, the current flows up or down. So I can reverse the direction of the current. And all I'm going to do really is energize the circuit, and you're going to watch the compass needles respond. Okay, so I'm building up some drama by again pointing out the long straight wire, the compass needles surrounding the wire. And then here's the switch. And right now there's no current in the circuit, and I'm going to close it. And did you see there the compass needles burst into action? So they've been influenced by the surrounding magnetic field. And if you look at least in these three here, they were kind of forming the concentric pattern. Now I've turned the circuit off, so they're going back to where they were. And now again, I switched the current, but in the opposite direction. And the current needles have moved in the opposite direction. And so you see the influence of the magnetic field from the current carrying wire. Now you might have noticed, right? You probably did. Might notice that the compass needles didn't just simply form concentric loops around the wire. They were influenced by the magnetic field around the wire, but they didn't simply form concentric loops. That's because there's the magnetic field of the current wire, but there's also the magnetic field of the Earth. So the exact pattern there was a superposition of the Earth's magnetic field that we live on and the current carrying wire magnetic field that we just generated. But I wanted to show you that a current produces a magnetic influence. And that experiment we just did there, I want to, it was the famous way that Hans Oersted discovered that currents produce magnetic fields. And he didn't set up an experiment like that and say, oh, I'm going to demonstrate to the class that currents make magnetic fields. He accidentally noticed that when he switched on a current, the compass needle orientated. It's fantastic, fantastic discovery. Okay, let me go back to sharing my slides. Okay, and let's go on to an example or an illustration of magnetic fields, magnetic forces for long straight current carrying wires. And specifically, what I'm going to do is use that equation we just met to figure out the an equation for the force between a pair of current carrying straight wires. So we're going to use the equation for the field to figure a force between two current carrying straight wires. So this is the situation I want to look at. Let me get the pen going again. And so my goal here, think of this as an example problem or example question. The goal is to figure out the force between a pair of current carrying wires. And I'm not going to figure out a number of newtons for the force between a pair of current carrying wires. I'm actually going to figure out an equation, formula for the force between a pair of current carrying wires. And I'm going to do it by putting together something we learned in last class, which was the relationship between the magnetic field and the force that it transmits, and something we just learned in this class, which is the magnetic field that's created by a straight current carrying wire. So what I'm specifically going to do, I wrote it out here. I'm going to determine the equation, formula, expression for the force between these two straight wires. This one upstairs here, this one downstairs here. So upstairs wire, I called it wire number 1, is carrying current I1. Downstairs wire, I called it wire number 2, is carrying current I2. These two wires are separated by some distance. I've called that distance D. And we're going to figure out the force between these wires as a function of the currents that are flowing in the wires and the distance between the wires. And to do it, we're going to use two things. This one's from this class. That the magnetic field, so that's B in this equation, that's created by a long straight current carrying wire is given by this equation here. So that's one thing we're going to use, and it was just on the prior slide. And then we're going to, I can't remember last week, but I'm going to pretend I can. Here's an equation from last week. This is the magnetic force that is exerted on a current carrying wire in a magnetic field. And this is the equation that we met last week. So this describes the force in a magnetic field. And this one upstairs describes the magnetic field of an electrical current. And we're going to put those two together to figure out this, this force that exists, and it's actually sketched in this picture in blue here, this force that exists between these two current carrying wires. As we do this, I'm firstly going to worry about the direction of the force, then I'm going to worry about the size of the force. So I'm going to separate the figuring of the direction and figuring the size into two separate parts. And when we talk about the directions, I'm going to use, just to make you really happy, the right-hand rule, two right-hand rules that we've met. The right-hand rule that we just met that told us the direction of the field of a current carrying wire, and the right-hand rule that we met in last class, which told us the direction of the force on a current carrying wire in a field. So I hope that's okay. So this is like part one. This is the direction of the magnetic force between the two current carrying wires. And then in the next slide, I'm going to do the magnitude of the force between the two current carrying wires. And the way I'm going to do it is I'm going to figure the force on wire number 1 due to wire number 2. We could have done the reverse. I could have figured the force on wire number 2 due to wire number 1. That's perfectly okay too. But I've just chosen, right? I was, thinking about this last night, and I thought, you know what? I'm going to tell them the force on wire number 1 due to wire number 2, due to wire number 2's field. Now, we all know Newton's third law, right? Forces come in pairs. So the force on wire number 2 due to wire number 1's field would be equal in size and opposite in direction. So we're going to figure out this force here in blue that I've now made red. Okay, so the first step to finding the direction is I'm going to find the direction of the field, the magnetic field, from current carrying wire 2 at the location of wire number 1. So why don't we all do this? Why don't we have a group project? We're all going to find the direction of the field at the location of wire number 1 due to wire number 2. So if we're all going to do this, it would be great if we were all doing this in class. But we're all doing it at home, or in I don't know, in the cafeteria or wherever we are. So I'm going to point my thumb in the direction of I2. So I'm pointing my thumb, I'm looking at that, and I'd encourage you to look at the slide. Point your thumb of your right hand in the direction of I2. If you're doing that, your fingers are they would be curling around the wire in such that they go into the slide below the wire and come out of the slide above the wire. And so the magnetic field above the wire is coming out of the slide. I hope that's okay. I mean, if it's not okay, you could put not okay in chat. But that is the right-hand rule for the long straight wire. It's going to tell me that the field comes out of the screen, the slide, above wire number 2, and would go in, we're not interested in it so much, go in below the wire. Explain again. Okay, so again, I've got this real problem that the camera's reversing left and right, but I am taking my right hand and I'm going to point that thumb, do this. Point your thumb in the direction of I2 on the slide, on the overhead. I have to believe your right hand now has your fingers kind of curling up towards your face. That is and remember the wire is kind of in the palm of your hand. So they're curling up towards your face above the wire. And if you loop them over, they will curl in away from your face below the wire. So they're coming out of the screen above the wire. They would be going into the screen below the wire. So that's how I got this direction for B. Once I've got B, I've now got that sort of problem from the prior lecture class, last Thursday's lecture class, of what is the force of a current in a magnetic field. So now if I want to find the direction of the force on I2, I would take the palm of my hand and I would point it in the direction of the current. So I'm going to take my hand away and look at the screen. I'm pointing the palm of my hand in the direction of the current. I'm going to curl my fingers in the direction of the field, which means that they would curl towards my body. And my thumb of my right hand is pointing downwards. And so that's the direction of the force. And so this part is the right-hand rule from last class. The first part is the right-hand rule from this class. And those two parts are explained here and here. And the consequence of this is that we just found that this wire I1 or 1 is being attracted by wire I2 or wire 2, and vice versa. If we did it the other way around, wire I carrying I2 is being attracted by the wire carrying current 1. Okay, I see in chat the request to do the second part again. So again, the second part of this direction thingy, for the direction of the force between the two wires, is that once you know the field at wire number 1, and you know wire number 1's current, you can find the force on it. So again, you point, this is my right hand, and I'm going to point the palm of it in the direction of the current. So that's towards the right of the slide. Then I'm going to curl my fingers in the direction of the magnetic field. So that's out of the slide. So it causes me to sort of tip my hand upside down, where my thumb is now pointing downwards, which means that the force is downwards, which means that the lower wire, wire 2, is attracting the upper wire, wire 1. And so these two wires attract. And this is actually a very famous discovery by a scientist, André Ampère, French scientist, who discovered that two like currents, we call these like currents because they're in the same direction, they attract one another. And actually, if you reverse one of the currents so that they're two opposite currents, two unlike currents, and do the same right-hand rule tricks, you discover that they repel one another. So it's actually interesting because if you remember electrical charges, unlike charges attract and like charges repel, or you remember magnetic poles, unlike poles attract and like poles repel. Here's the reverse. Like currents attract one another, opposite currents repel one another. So that's what I concluded here from all this right-hand rule work. Okay, I hope you enjoyed that. Now the magnitude. And I think the magnitude is actually easier than the direction. When we did the direction, we first figured the direction of the magnetic field from wire number 2, and then we figured the direction of the force on wire number 1. When we do the magnitude, we're first going to figure the magnitude of the field due to wire number 2. And then we're going to figure the force that it creates on wire number 1. And so that's what I'm trying to do here. So look at this equation. B2 is the magnetic field created by wire number 2 and current number 2. So that's the strength of this force B2 that is created by this current I2 at the location of wire number 1. So a distance, that wire is a distance d from the source of this field, wire number 2. So that's that expression. If wire number 1 is immersed in field number B2, so here's the field that wire number 1 is immersed in, it will experience a force, I called it F1 because force on wire number 1, that is the current in wire number 1, the length of wire number 1, times the field that it's immersed in. Actually times a sine theta, but theta's 90, the direction between the current and the field. And so that's actually just 1. So upstairs is how the current makes the field, downstairs is how the field makes the force. If you plug the field equation into the force equation, you get this formula here. And I divided through by the length of wire number 1. You get an interesting equation, actually. It's the force per unit length, so that's newtons per meter, that's exerted on wire number 1 due to wire number 2. And you see it depends on things you might expect. The product of the currents. So if you make either current bigger, you're going to get a bigger force. If you make either current smaller, you're going to get a smaller force. It also depends on the separation between the wires. Put the wires closer, you're going to get a bigger force. Pull the wires further apart, you're going to get a smaller force. And so this is the answer to the second part of this problem. What is the force? Okay, I'm looking in chat. When you say attract and repel, does that mean the currents will actually move towards or away from each other? Yeah, I do absolutely mean that. And I'm going to demonstrate it right now. Those wires are pulled together or pushed apart depending on whether the currents are in the same direction or in the opposite direction. Let me just answer it with a demonstration. So I'm going to share a different screen. Okay, so on this, no, you're not seeing a different screen, are you? On this screen, let me just stop the video a moment. I'm going to show you two wires, and I'm going to show you their attraction and repulsion. But firstly, I'm showing you how I'm going to switch on and off the current in the two wires. So what I'm showing you is there's a switch, if you can see my pointer here. And flipping this switch between these two positions reverses one of the currents. So in the lower position, I can make this arrangement of the two wires where the wires have currents flowing in the same direction. In the upper position of the switch, I can make this situation where the currents are flowing in opposite directions. So this switch here controls whether it's like currents or opposite currents. And then there's a switch upstairs here that actually switches the current on or off. And so I'm just going to show you that to begin with, and then I'm going to, arrange it so the currents flow in the same direction and turn the circuit on. We'll see the attraction. Arrange it so that the currents flow in the opposite directions. Turn the circuit on, and we'll see the repulsion. So we'll just watch those two cases. It's just going to come up here. So here's the two wires. The current's not on right now, and I'm about to switch it on. And I'm going to switch it on in the same direction. And look at that. I mean, that's not a small effect. They basically became one wire. Now I switched it off, so it went back to where they started. Now I'm going to do the opposite direction. Look, they're trying to get away from each other, but gravity's pulling them back. And so they're pushing apart, being pulled back by gravity. And so that's, I think, a great demonstration of attraction repulsion between like and opposite currents in straight wires. As I say, it was a very famous discovery, explanation by this French scientist Andre Ampere, and we call current amps. So that's part of the story. Let me go back to my slides. And now I want to talk about the magnetic field of a current carrying loop. This will be pretty quick, I think. I've got to get my pen working. So that'll slow it down. Okay. Now this is an interesting slide. I mean, it's quite artistic, but it also is physics interesting, science interesting. I got sketches of two different fields. I got sketches on the left-hand side of the field of a bar magnet. This is something we met before. And I got over here on the right-hand side, sketch of the field of a current loop. So that's the new thing. Now, you remember the field lines of a bar magnet. So here's the bar magnet. I'll outline it in red. And as you recall, it's got a north pole, it's got a south pole. And as you'll recall, the field lines come out of the north pole and loop back towards the south pole. So they form these loops. And so that's the pattern of the magnetic field of a bar magnet. Field lines coming out of the north, field lines returning to the south. The field's strong near the magnet, and the field gets weak far from the magnet. Now, this is the current loop over here on the right-hand side. So imagine it as a loop of copper wire or something. And the current here is flowing at the front of the loop, is flowing over away from the left towards the right. So on the left-hand side, it's coming out of the slide. On the right-hand side, it's going into the slide. So it's going around this direction here, like my pen. The magnetic field of that current loop has field lines coming out of the current loop above the current loop and returning and heading into the current loop below the current loop. It's a field that's strong near the current loop, and it's a field that gets weaker far from the current loop. And that's exactly what the field of the bar magnet looked like. So we could call this the north pole of the current loop and the south pole of the current loop, because the patterns of these field lines are the same. They're coming out of the top, they're returning to the bottom. They're strong near the magnet or near the current loop. They're weak far from the magnet, far from the current loop. Now look, if you spot that those two patterns of fields are so similar, are the same, the way to make the same magnetic field patterns is to have the same current flows, the same geometry of electrical currents. So what this is actually telling us is, well, look, in the loop of wire, we know the current is flowing in a circular path. It means that in the magnet, there's actually kind of electron currents, the subatomic building blocks that are also flowing kind of around the body of the magnet in a circular path. And so we've learned something about the bar magnet as well as learning something about the current loop. I think that's really nice. And I say that here. Both these fields actually originate from the same pattern of currents. That's why you get the same pattern of magnetic field lines. They originate from a current loop that's flowing out of the slide on the left and into the slide on the right, around and round and round in a circular path. Okay. Now, in general, the equation, the formula for the field of a current loop or field of a bar magnet is a very complicated equation. We're not going to write down the field of a general field of a current carrying loop, but I am going to give you one equation. Is this equation here. This equation here. It's the equation for the strength of the magnetic field, the size of the magnetic field at the very center of the current loop. So if you look at this current loop, that current loop is characterized by some current that's flowing in the wire and some radius of the wire. And those I've given the names I for the current and A for the radius of the wire. The magnetic field at the center depends on the current, as you might expect, depends on the radius, as you might expect, and it depends on this in this way. So the bigger the current, right, then the bigger the magnetic field. Of course, that makes perfect sense. The larger the radius, the smaller the magnetic field at the center. That probably makes sense too. And then, of course, you see our friend here. This is the magnetic permeability of free space. That's quite a mouthful, but it means the characteristic strength of the magnetic interaction. And so, of course, the magnetic field depends on sort of the characteristics. Magnetic fields and magnetic forces depend on the characteristic strength of the magnetic interaction. And so this is a useful equation, but it just applies, let me be clear here, to the field at the center that comes out of the top of the loop or points into the bottom of the loop. And that field at that center has this strength. I think I've got an example of using that equation coming up. Quick example. And here it is. So in this example, we've got actually two current carrying loops. You've got a larger radius loop, that's the outer loop. This radius is called R1, this carrying current I1. And you've got a smaller radius loop, its radius is R2, is carrying current I2. And we're told the radii of the loops, and we're told the currents that are flowing in the loops, and we've got to find the field at the center of the loop. Now, part of this is using these equations for the field at the center of the current loop. The other part of this is superposition principle, where the total magnetic field is the sum of the magnetic fields from the two current loops. We met that superposition principle when we talked about electricity. We're meeting it here again when we talk about magnetism. And then finally, the third part, you'll be really pleased with this, is that there's another right-hand rule for current loops. A right-hand rule that tells you the direction of the field at the center of the loop from the direction of the clockwise or counterclockwise circulation of the current around the loop. To show you that, let me just quickly nip back to the prior slide if I'm capable of doing that. So the rule for finding the direction of the field at the center of the current loop. So the question is this field up or is this field down? So you take your right hand again. Looks like my left, but this is really my right hand. Now I'm going to put that right hand next to the slide, next to the overhead. And I'm going to curl my fingers this time in the direction of the current. So if I'm going to curl my fingers in the direction of the current, they've got to come out of the slide on the left and would head back into the slide on the right. If I curl my fingers in that way, my thumb is pointing upwards. And my thumb is the direction of the magnetic force. So there's a right-hand rule for the magnetic field. There's a right-hand rule for the magnetic field of the current carrying loop. And that right-hand rule is that the fingers curl in the direction of the current and the thumb points in the direction of the field. That's actually the reverse of the right-hand rule for the current carrying straight wire. Remember there, the thumb pointed in the direction of the current and the fingers pointed in the direction of the field. Okay, so that brings us back to figuring out the field in this situation. In this overhead view of the two current loops, one of them, the current is flowing counterclockwise, and one of them is flowing clockwise. So I2 is clockwise and I1 is clockwise and I2 is counterclockwise. So if I want the direction of the field due to I2, the counterclockwise one, I would curl my fingers counterclockwise and your right-hand thumb points out of the screen. So its field is outwards. If you want the field of direction for I2, you curl your fingers in the direction of I2, so that's clockwise. Your thumb points inwards, so the field is inwards. So it's important the two currents are opposite directions. So not surprisingly, the two fields are opposite directions in this case. And so with that information, here's my calculation of the net magnetic field at the very center of the current loop. So what's B here? Let's figure it out. And we're figuring it out using this numerical information. We know the two currents, I1, I2. We knew the two radii, R1, R2. And we're figuring out with the idea of superposition that the total magnetic field, B, at the location of the center of the two loops, is the superposition sum of the two magnetic fields B1 and B2 of the two individual current loops. And so we just got to combine those. Now, when we combine them, the way I'm going to do it here is that the magnitude of the resulting field, B, is going to be the difference between the magnitudes of the individual fields, B1 and B2, because they're in opposite directions. So they're partially canceling each other out. And I chose a sign convention, right, where a positive field would be out and a negative field would be in. And so in this case, right, because the current I1 was clockwise, its field is in to the overhead. Current I2 is counterclockwise, its field is out of the screen. Anyway, I then just plugged in for B1 and B2 for the magnitudes of those fields, those expressions. I'm plugging in that at the center of a current loop, the field is given by mu naught over 2 times the current in the loop divided by the radius of the loop. So this would be either the field for 1 or 2. It will be either the current in loop 1 or 2 and the radius of loop 1 or 2. And so I plugged in those expressions here. Mu naught over 2 is a common factor that you can pull out. The current to radius ratios are not common factors. They're different currents, different ratios. But then I just plug in all these numbers, right? I didn't go through all the trouble of writing it out. I was getting tired. I plugged in the numbers and I get minus 5.2 microteslas. So the field is actually into the screen, not out of the screen. It's because the field of the larger loop, which had the larger current, is actually a bit stronger. The field due to the smaller loop, which has a smaller current, is a bit weaker. So if you know, this is a battle of the currents, right? I2 is 1 over I1, and sorry, I1 is 1 over I2, and the field ends up pointing in the direction of I1 because it's slightly stronger, somewhat stronger. Okay, can I go back over the this question in chat? I'm not just talking to myself randomly. Can I go back over the right-hand rule for the magnetic field of a current loop? Yes, I can. I can, but I'm going the wrong direction. Let me go back to this. So again, I think you got to do this with me. I can't do this on my own. You have to try it yourself. So you're going to grab your right hand. And you're going to put your right hand, I've put it right next to the slide here that has the current loop on it. So here's the current loop, and I put my right hand just over here on the right of that. And I put my hand so my fingers are curling out on the left-hand side of the loop. So the tips of my fingers are pointing out of the screen over here on this side. And the palm of my hand is kind of pointing in on this side. And that's the direction of the current flow. So I should have put this, I guess. The current's flowing in on the right, and sorry, I've really messed this up. the current's flowing out over here and in over here. So my fingers are coming out on the left and my palm's going in on the right. And the only way I believe you can do that, unless you've got some hand that's different from my hand, is that your thumb is pointing upwards right now. So that's the direction of the field, is upwards. So I hope that makes sense. Last topic. Magnetic field of a solenoid. So let's talk about the magnetic field of a solenoid. And we normally talk about what we call a long solenoid. You'll see what I mean by a long solenoid. But here's a solenoid. So a solenoid is just like a chained connection of many loops. Just a whole string of many loops. So we just talked about one loop and the field at the center of one loop. Now we're talking about wiring up many of these loops and the field in the solenoid, inside this sort of chamber that's created by these loops of wire. Now, when we talk about solenoids, we characterize a solenoid, the geometry of a solenoid, by various quantities. So we will talk about the number of turns of the solenoid. So N is the number of turns of the solenoid. So in this case, this solenoid, like 1, 2, 3, 4, getting bored, say 15 turns. 15 turn solenoid. We'll talk about the length of the solenoid. So look, here's the length of the solenoid. That's something about the geometry too. We can talk about the radius of the solenoid. You know, that will determine how small or large the cross-section inside the solenoid's chamber is. And so that's R and this length was L. And sometimes even, I didn't mention this on the slide, but we sometimes talk about what we usually call lowercase n. It's uppercase N over L. It's the number of turns per meter of the solenoid. So we'll see that later on. And then, so that all those describe the geometry of the solenoid. And then, of course, look, you can have a solenoid, but it's not switched on. It's not going to make any magnetic field then. Or if you turn it on, you'll get a current in it. And so here's the current I that's flowing in the windings of the solenoid. And that current, you know, goes in at one end and works its way all the way down these windings, comes out the other end. So it will know how many turns there are. Okay, so that's the geometry of the solenoid. That's the current flowing in the solenoid. And now I want to show you the expression for the field of a solenoid. And I also want to say something about the direction of the field of a solenoid. So firstly, on this slide, over here on the left is kind of a picture of the field lines where I made a solenoid by winding many turns of wire, but the windings aren't very closely packed. And you see that you get a kind of complicated field that at the ends looks like the fields of a single turn. So this slide on the left is telling you how I'm morphing kind of that single loop of wire in its field into a solenoid's loop of wire. If you do that many, many turns and pack those turns together, you actually get this field on the right. And this field starts to look interesting, simple. So in this field, over here on the right, this is actually both of these equations. This is the field, this equation upstairs here is the field equation for the strength of the field inside this solenoid. Over here on the left-hand side, here's the right, here's the left-hand side. This is approximately the field inside this solenoid. So if you've got a solenoid where the windings are closely packed, then you approach this equation for the field. It becomes nice and simple. If you've got a solenoid with loosely packed windings, you might have approximately that field. And I'm just mentioning that because that's kind of how you construct a solenoid. But look at this equation. It's really rather simple. This field inside the solenoid, it's in proportion to the magnetic permeability, which makes sense. It's in proportion to the current, which makes sense. More current, more field, less current, less field. And then it just depends on how closely packed you pack the turns. This little n here is the number of turns per unit length. And so that's what's governing. That's the geometry, the part of the geometry that's governing the field strength in the solenoid. The more closely you pack those turns, then the stronger the field gets. The greater the number of turns per unit length, the greater the field will get. And so that's what you're seeing as I'm walking from the picture on the left to the picture on the right. I'm more closely packing the turns, and I'm correspondingly increasing the magnetic field by more closely packing the turns. I'm also making the field more uniform. It's approximately uniform inside over here on the left. It's got much more uniform over here on the right-hand side. And so that's actually how we make a uniform magnetic field. We make it with a solenoid. Often in an application, you want a uniform magnetic field, and this is how we make that uniform magnetic field. And I would look at those equations and think, what features of the solenoid does the field depend on? And maybe what features of the solenoid does the field not depend on? And think about that, just think about that simple equation. I got a quiz question coming up. Okay, so I think almost everybody has answered this question. We've just got a few minutes left. So let me just explain the answer to this. I was trying to avoid answering the two questions in chat that were actually this question. So the equation for the magnetic field in the solenoid was mu naught times the current times lowercase n. So a very simple equation, mu naught I n. So that equation for the magnetic field depends on the current, which makes sense. More current, more field, less current, less field. It depends on how closely we're packing together the loops of wiring building the solenoid. So it depends on number of turns over length, which is how closely we pack the turns. And that makes sense too. I think if you put a bunch of loops of wire closer together carrying a current, you're going to build up the magnetic field. If you stretch them apart, you're going to have less magnetic field. But it didn't depend on the radius. And the field inside the solenoid does not depend on the radius. So the field in the solenoid on the left, which has the smaller radius, is no different from the field in the solenoid on the right, which has the larger radius, because those two solenoids, although their radii are different, they have the same currents, they have the same number of turns, they have the same length, they have the same number of turns per unit length. Now, the fields are the same strength. Now, the field is occupying a smaller region in the smaller radius solenoid. The field is occupying a larger region in the larger radius solenoid, but the fields are only the same, the fields are the same size. And so that's the answer to that question. Okay, so let me just summarize today's class. We've moved on in today from last class where we talked about the force on a current due to a magnetic field. Here we were talking about the magnetic field that's created by a current. And we really focused on the three most interesting, most common situations. The field of a long straight current carrying wire, and we looked at an example problem with that. The field of a single current loop, we looked at an example problem with that. And the field of a long current carrying solenoid, which is many current carrying loops. And we looked at a question involving that.